We have all been there. It is 2 in the morning, you are staring at the ceiling, and right outside your window, a single cricket is relentlessly broadcasting its presence to the entire neighborhood. It is easy to write that repetitive scratching off as a sleepless nuisance, usually followed by the vague memory from middle school biology that the insect is down in the grass rubbing its legs together. But if you listen closely to the rhythm, you will realize this is not random noise. That solitary insect is functioning as a fairly precise biological instrument, actively broadcasting real-time environmental data into the night air. Nature has embedded a remarkably accurate thermometer right in your backyard, and we routinely ignore it. To actually read the data it is transmitting, we first need to look at how that sound is manufactured. Let's clear up the biggest misconception first. Crickets do not make that sound with their legs. The audio is generated entirely by their wings. The scientific term for this acoustic process is stridulation. If you zoom in on a male cricket's wings, you will see they are highly specialized. The bottom of one wing features a row of small, ridged teeth called the file. The other wing has a hardened, sharp edge known as celsius. When a male cricket claims a patch of grass or attracts a mate, he raises his wings and drags the screeper across the file. He is effectively playing his own body like a biological violin. Every single chirp is a deliberate, biomechanically engineered action, but the insect does not actually control the tempo of its own song. That rhythm is dictated by an invisible external force. Crickets are cold-blooded creatures. Because they lack the internal machinery to regulate their own body heat, their baseline physical state is entirely at the mercy of the ambient weather conditions. As the night air warms up, the heat triggers a surge of chemical reactions within the cricket's metabolic system and muscle fibers. These rapid reactions force the insect's muscles to contract faster, scraping the wings more frequently and driving the chirping tempo upward. When the temperature drops, the exact opposite happens. The cold sluggishly throttles the cricket's metabolism, slowing the muscle contractions and creating a much longer delay between every single chirp. The acoustic rhythm echoing outside your window is a direct physical manifestation of the invisible heat in the air around you. A physicist named Dolbear mapped out this exact causal chain back in 1897. He realized that because the cricket's biology was entirely dependent on thermodynamics, the relationship could be strictly quantified. He published a set of formulas to decipher this biological data, an equation we now call Dolbear's law. To take a reading, you first need to isolate the sound of one specific cricket. Then you simply count how many times it chirps over a span of exactly 25 seconds. Here's the math for Celsius. Take your total chirp count in 25 seconds, divide by 3, and add 4. For example, 48 chirps divided by 3 is 16. Add 4, and you get exactly 20 degrees Celsius. With a stopwatch and basic arithmetic, a territorial meeting call becomes verifiable meteorological data. Standing in the dark counting bugs for nearly half a minute can feel a bit tedious, so there is a much faster shortcut you can use. This graphic breaks down the simplified version. You just count the chirps for 8 seconds, and then add 5 directly to your total. It requires far less attention span, and it will still give you a highly accurate estimate of the ambient temperature in Celsius. So the next time a relentless insect keeps you awake at night, try listening to it differently. Instead of burying your head under a pillow, grab your phone, set a timer, and test the formula for yourself. When you understand the invisible thermodynamics at play in the background, a frustrating noise becomes a precise, interactive piece of the natural world.